Good morning, chemistry students. It's me, Mr. Cheney, with another brilliant tutorial. This is the third installment of the annotations of notes in our first chapter having to do with the conservation of matter. So on this one, we did not have any vocabulary words, so we went through as a class and made some notes as I read through the chapter material. So if you weren't here on the day that we did that, this video is for you. So here we go. Conservation of matter, a conceptual model of matter. Conceptual models of matter have some similarities to and some differences from models of energy. Like energy, matter can be tracked as it moves through and among systems. Matter, like energy, is also conserved in chemical reactions. It can neither be created nor destroyed. So we're highlighting in our notes here, unlike energy, however, matter consists of physical stuff, so you can touch it and hold it. You can also measure the quantity of matter. This is mass. So I want you to highlight this is mass. In some situations, it is sufficient to treat matter as a continuous substance where bulk characteristics provide enough information. In chemistry, however, you must work with models of molecules, atoms, and their subatomic components, protons, neutrons, and electrons to understand and predict chemical behavior. So in this chart right here, these are the annotations that we need to do. You're going to be circling the word atom and the word electrons, and we're going to highlight the particles of an atom: protons, neutrons, electrons, the words negatively charged for electrons, and the phrase nearly all of the mass in the atom in the nucleus. Now just to back up for a second, where do we find these notes? This is the third one, so in Google Classroom you are going to find these in the section here. So this was our first notes section, this is our second, so this had 11 words. This had 3, and then this is the one right here, conservation of matter, where we're making our notes now. So going back, once you've made those notes, click next. And this chart right here we did not go over in detail, no notes there. Moving on to the third page. So now open and close systems. So highlight and circle the annotations that you see. So thermal chemistry is the study of the heat exchange between systems and their surroundings. In an open system, so circle that word, open system, such as an open saucepan with boiling water, both matter and energy are transferred to the surroundings. However, if you put a lid on the saucepan and create a closed system, circle the word closed system, matter cannot escape and it is instead contained and conserved in the system. If you added the amount of water vapor in the pot to the liquid water that cooled and condensed on the lid, you would find that they are the same as the amount of the water that evaporated. In an isolated system, so circling the words isolated system, and such as a thermos, highlight thermos, where the sides are insulated and a lid is screwed on tight, no energy or matter is transferred to the surrounding areas. So here's just a graphic representation of what that paragraph went over. Open system versus closed system versus isolated system. Next page. Measuring the flow of matter. We did not go over anything on this section, so no notes there. Next page, we had some notes, just a highlight right there. So in combustion reactions, oxygen gas reacts with a molecule, often releasing energy in the form of both heat and light, a flame. So the fuel that burns is often a hydrocarbon containing atoms of both hydrogen and carbon. In all cases, matter is conserved during the reaction, so make sure you highlight that sentence. The same numbers of atoms exist before and after the combustion reaction. In the combustion of propane, oxygen reacts with propane. The products of the reaction depend on the amount of oxygen present. But in all cases, the numbers of carbon, hydrogen, and oxygen atoms are conserved. Okay, so that was the only notes on that page. And this is our last page of notes, so it has to do with combustion and work. And this all leads up to the rocket lab. That's the assignment attached to this. So combustion and work. The energy of combustion is used to generate heat and light, but it can also do work. Work is the product of the net force on an object and the distance through which the object is moved. Work has units of energy, so it's measured in joules. So let's talk about rockets, because the lab is about rockets. So we're going to circle the word rockets, and then you know that the expansion of hot gases during combustion can be used to push a piston, and that if several pistons are fired with the correct timing, they can power a car. So we talked about that in one of the other sections where potential chemical energy was the gas, and then we put it into the gas tank, and then from the gas tank the fuel pump pushes it through to the engine, and the whole process of an engine working to make your car move forward. So another more direct application of mechanical work using combustion is a rocket. So in a rocket, solid or liquid fuels are burned to reduce hot gases. So you're going to highlight that sentence right there. Because the gases take up a much greater volume than the fuel, the rocket gets pushed in the direction opposite to the direction in which the gases expand. That is how NASA rockets reach the Moon, Mars, and other planetary bodies. And I believe that's the last section of notes. We didn't go over this because Bushry will cover that in physics. And we touched a little bit on nuclear reactions, but no notes there. And that is it. So once again, this is for the people who were not here when we took notes for section 3. Make those annotations and click the turn in button, the blue one in the top right, when you're finished. And that's it for now. I'll see you back in class.